Good afternoon. Welcome back, quantitative analysis students. This is Mr. Marquetta, and I'm here to help you today with Chapter 11, where we study derivatives of exponential and logarithmic functions. Today is July 22nd, and we're going to go through all the motions of what it means to take a derivative of a log and what it means to take a derivative of anything to a power. First, let's talk about logarithms. What is a logarithmic function? So what do we mean by a log? Now, it is kind of important that we already understand what a log is and how logs work. Some students may have a little bit of a, they might not be able to remember it, or they might have a background where they didn't really study that very much in school. So before we start talking about derivatives of logs, I'd like to explain for you the connection between logarithms and exponents and how you can use one to get the other and vice versa. Starting with the general concept that we have here of y equals the log base to a of x. Okay, this is something that we like to call logarithmic form. And by the way, at this point, I'll ask you to make sure that your view is changed to speaker view so that you could see what I'm writing. This is something we call logarithmic form. This statement is relating three different quantities, a and x and y. The easiest way to understand the relationship between a and x and y is to look at the same statement but as an exponential form. The exponential form is a to the y equals x. Now, this is something we all understand. We don't have problems with this because we understand exponents. But the word log is ultimately an exponent concept, but it's kind of that the variables have been rearranged and put in different positions. Let's take a case that we know and are familiar with. For example, 3 to the fourth power equals 81. That is true, and we all believe that. If that be the case, we can say this is the exponential form of that idea. The logarithmic form of that idea is the log base 3 of 81 equals 4. Notice that the answer 4 is actually the power, which is why people often argue that a logarithm is nothing more than a power. In fact, whatever this quantity is here, y is the power in the statement ultimately anyway. So one way to think about logs, if you're trying to figure them out, is the way that this is down below and a smaller font, like a subscript, and this is a regular average size font, there is an upwards feeling like this, like you're moving upwards. You can ask the question, 3 to the what power is 81? And in that regard, if you think about it, it's 4 that belongs there. So whenever you see a logarithm, you can figure it out really easy. Some of them can be figured out really easy if you think of that idea, like the log base 2 of 8. You should be able to look at that and figure out that's 3, because if you think about this, the arrow I was telling you, the question is 2 to the what is 8? And the answer is 2 to the 3 is 8, so the answer is 3. Okay, so what is a logarithm? A logarithm is a way for you to express an exponent. It's an alternative method, an alternative way to make a sentence about an exponent. That's what a logarithm is. And ultimately, the logarithm itself is the exponent. It's the answer of what would you have to raise this to in order to get this. That's what a logarithm is. It's a power. All right. So I hope that you remember that from back in your high school lessons. That's what a logarithm is. Now, in that regard, if you were to go and graph logarithms, it would look kind of like this. And you could see it's got a function that has the y-axis. It never touches the y-axis, and it goes through the point 1, 0. In other words, this is our basic concept of a logarithmic graph. So you can, of course, use Desmos to graph logarithms. All you have to do is type in log, and it knows just what you're talking about. While we're in the conversation about logarithms, there are two special kinds of logarithms that we're going to use a lot, so I need you to be familiar with those, the natural log and the common log. The way that those work is we have two important numbers that are really special that we like to use a lot. The first number I want to talk about is a number called E, and it's based on a number that was discovered by a German mathematician whose name is Euler. Euler is spelled like this. As Americans, we may feel that this would be pronounced Euler, like a ruler, but in German it's Euler, and his name is starting with an E. And when he discovered this wonderful number, he named it after himself, and they call it E. E is approximately equal to 2.7, and it is a number that is the best representative of a base for natural logarithms for different chemistry cases and physics cases. There's also other big purposes for E in counting and all different kinds of math. When you start thinking, what would be the ideal number? Often E is the answer. And there's a special formula for E that's hard to understand, but it's irrational. It goes on forever and ever like pi does. But E is one of our most important bases that we like to use a lot. Another one that we like to use a lot is 10 because it's our base for the decimal system. So if we wanted to say log based E of x, instead of saying log based E, we write ln x, which means log natural, or the natural log of x. And we can assume when we look at this, even though this is kind of funny looking and the word log is not there, this is a logarithm. It happens to be a specific kind of logarithm. It's called a natural logarithm, and it is the equivalent of log based E of x. All right. Last but not least, the common log is when we say that the log has a base of 10. So if I wanted to say the log base 10 of x, I could have said that this way, log of x. Notice there's no base written at all. If you don't write a base at all, we assume the base is 10, and we call it a common log. Okay, so generally logs will always have a base. Log base 2, log base 5, whatever. But if you see a log with no base, the base is 10. And if you see a log written this way, without the word log, but instead the letter L and then N, we are to assume it is a logarithm with a base of E, the E is being the number that has been discovered by Euler, the German mathematician, approximately 2.7. Okay, so this is a base E, this is a base 10. This is a natural log, this is a common log. All right, so now that you got all the scoop and all the gossip about logs, that's the whole story that you really need to know more than anything about it. Now that we've got that concept, there are some little log rules that follow that we're supposed to be familiar with. And in this situation, if you haven't studied logarithms and this is the first time you're seeing it, I'm going to ask you to go back and study them a little bit more using your textbook. You can also use other resources like Google or YouTube, just to familiarize yourself with properties of logarithms. I'd like to zoom in on these properties of logs and talk about them. First, let's talk about how these are two sets of statements that all say the same thing, okay? What they're saying is a logarithm, whether it's a base of E or a base of A or a base of anything, it still follows the same properties. If you look at part 1, they're the same thing, except in part 1, the base is A on the left. In part 1, the base is E on the right, but they're stating the same things. So let's talk about how each of these works. I'd like to focus on them one at a time and just have a conversation about them so that you're familiar with the general concept there. So let's start with this one. I don't know if I like the way that looks. Hold on a minute. Let me change that. That's nicer. All right, we'll start with this one. What does this say? This is saying if ever you have a logarithm of something to a power, what you can do, as long as the base and the argument match, meaning as long as this part right here, see that A, and then the main thing, see that A, how they match? It's almost as if they cross out. I've seen students act like they're crossing them out like this, like the A and the other A cancel out that way. You know, if you think of it that way, if you think of it that way, then it kind of looks like they cancel out and you're just left with X. The same thing happens here for this one, because in this scenario, we have a base of E. In this scenario, we have a natural log, which already has a base of E, and then we have E to the power of X. So in the same way, they kind of knock out and X is left. This is the first important rule, and you can apply it to any kind of logarithm. If the base and the argument match, just take the exponent. Next, if you find yourself looking at a combination like this, where you have A right there, and then you have it to the log based A. So look at how it's A to the power of log based A. It's not that different than a log-based a of a to the power of. Say they both turn out being x. Those are the two scenarios where you can kind of knock things out and get a simple answer. The same thing is happening here. These two have the same concept, that the base and the power are the same thing. Here, the power is the natural log. The natural log has a base of e. The e is the base to the power natural log. They knock out and you get x. So parts 1 and 2, these are the cases where you see situations that you should know to just cancel things out and you wind up with just x. Next, for numbers 3 and 4, I'm going to skip those for a minute. I'm going to jump ahead to number 5 for a minute because number 5 is easier to grasp. Let's talk about that for a minute. We're trying to tell you if you ever take the natural log of something to a power, you could take that power and bring it to the front as if it was a multiplier or a coefficient. It sounds very familiar to the power rule of derivatives, right? Because you've studied derivatives. But notice here, what's happening is my exponent, which is right here, the p, is becoming the new multiplier out front, which is right here as p. Same thing happens with natural logarithms or common logarithms. If you have something to a power, you may take that power, bring it out to the front, and make it the coefficient. That is not taking the derivative of it. That is ultimately just rewriting the logarithm with a logarithm-based property. So when it's time to take derivatives, please remember, it may be helpful to take the exponent off of the log, but remember, when you take an exponent off of a thing like this, like a log, you put it right in front and it doesn't change the quantity and is not taking the derivative quite yet, all right? Then the last batch of important properties we want to talk about are the multiplication and the division cases. Take a look here at the way this one works. Here I have the product mn. See it? So we write the log of m and the log of n. Now notice what we're using here for this. We're using plus. I'm trying so hard to make a plus sign pop out there. You all know what I'm talking about though. But anyway, what we're saying is that if you see a product like the log of m times n, then what you're supposed to do is write the log of m plus the log of n. So can we remember that inside the argument, if you're multiplying m times n, when you can write it out, put the log on both of those two things being multiplied, but put a plus in between. This looks a little bit like maybe the distributive property or like a stretching out. But remember that since it's logarithms, it follows a certain special pattern that if you see multiplication, you can split it, the word log to each thing, but you have to put a plus in between. In the same way that multiplication and addition increase ideas, division and subtraction decrease ideas. So look at this case here. Here we mean to divide. There you go. Here we mean to divide. So we'll put the numerator and we'll put the denominator. But since we're dividing, instead of using a plus, we're going to use a minus, like that. And as I said earlier, again, you could just go ahead and apply all of this, right, all over again to natural logs or common logs. It's the same idea. Again, I don't know why they gave it to you these two different ways. We could have just given it to you base A because natural logarithms are another example of base A. They're just written a little tiny bit different. But ultimately, the 5 important rules you need to know about logs, guys, are if you have the base and the arguments the same, you take it as the exponent. That's this one. If you have a base to a natural log with the same base like this one, you just keep the what's remaining, which is the x. If you're multiplying two things, you can write them separately with a plus sign. If you're dividing both things, you could write them separately with a minus sign. And if you're taking a log to a power, you could take the power out to the front as if it was a multiplier. Okay, so these are old rules that we assume that you already know and you're already real well versed in. And the truth is, not everybody's really well versed in it. It's okay if you're a little bit shaky on them or if you don't remember them very well. But I'm going to ask you for today's lesson and to get familiar with them again or to refamiliarize yourself. It is important that you're comfortable with all of these concepts to be able to go on and start doing derivatives of logs. All right. Now, let's talk about taking derivatives of logs and taking derivatives of and what it looks like. Now, first, let's talk about the derivative of the natural log. The derivative of the natural log, which I thought I had here somewhere, and it looks like I don't actually. Nope, don't think I do. All right, I'll show you just what it is then. Here's the idea of the derivative of a natural log. All right, so the derivative of the natural log of x is 1 over x. And the chain rule can apply here because if you have the derivative of something here that's not x, you write 1 over that something and then multiply by the derivative of what's inside. So we have some basic examples, but before we, and like for example, how about take the derivative, y equals the natural log of 5x cubed plus 2x. Okay, well, like we said, the derivative is going to be 1 over that. But don't forget to multiply by the derivative of what's inside. This time that's represented like this. So to find derivatives for natural logs, it's actually really very straightforward. All you do is literally take the reciprocal of what's in the parentheses. It's the flip of this. There you go. Now, because of the chain rule, don't forget to multiply by the derivative of what's inside. What's inside here is this binomial. The derivative of that is written here. This is the correct answer for what the derivative is of the natural log of that function. Let's do a couple more examples. In your PowerPoint, the next example that they're showing, example 1, is y equals x cubed plus 3 natural log x. Find dy dx. Okay, so if you want to try to find dy dx for this function, the way you should begin is by looking at the function and trying to classify it already. All right, so up front, it looks like it's a addition, the two things being added together here. So I'm going to apply the sum rule or the addition rule, which means I could take the derivative of this separately and the derivative of that separately. So let's start with x cubed. We all know the derivative of x cubed is 3x squared. How do we figure out the derivative of 3 ln x? Well, remember the coefficient rule. I'm not going to need to worry about the 3, so let me write the 3 again. And now, what is the derivative of ln x? We told you it's 1 over x. This is the solution we're looking for. If you want, you can clean it up a little bit like this. Because remember the 3 is over 1 and it becomes a basic multiplication case, but either of them really is acceptable. It doesn't matter which one you use. Let's take a look at another case. Here we have natural log of a trinomial. Okay, so we're trying to figure out the derivative of this function. And as you can see, in this function, we have another basic example of natural log. To get our answer, we're going to go right in with knowing that the derivative of a log is the 1 over what you see in the parentheses. So the derivative this time, f prime of x, can be found as 1 over that quantity. But then don't forget times the derivative of what's inside, and that's because of the chain rule, which is 4x cubed minus 3 there. And to make it a little bit nicer, remember this is over 1. We can make it look like one big fraction, like so. All right, that's example 2a for your illustration purposes. I hope that makes sense. Okay, that's what we mean by f prime of x there using the natural log. In example 2b, we have a very similar case, except we have a multiplier out front. We're telling you f of x equals 1/3 natural log of the quantity 2x to the 6th minus 3x plus 2. So for this question, again, we can apply the coefficient rule, which is, let's forget about that 1/3 for a minute and focus on the rest of it. So the derivative f prime of x now will be 1/3 times, and now to take the derivative of the natural log, you have to do 1 over that quantity. And then because of the chain rule, don't forget, multiply by the derivative of what's inside. This time that is 12x to the 5th minus 3. Now, to clean this one up, you could take the 3 and kind of either distribute it through everywhere or just write it as distributed like this. And then on the top, give it that binomial up there, 12x to the 5th minus 3. This is a fine derivative here. You could say it that way or the other way, and I'm sure that WebAssign will accept it in either way. So that's up to you, but you should be familiar with all the different, how to crunch together the algebra and make it come out correctly. All right, guys? The next example, and that's example 2b. Our next example, 2c, turns out looking like a fraction. Let me show you what I mean there. Example 2c is going to be g of x equals the natural log of 2x plus 1 all over 2x plus 1. To answer this question, what I need to do is first recognize up front that this is not just a logarithm, it's actually a quotient, and apply the concept of the quotient rule to it up front. So remember the quotient rule. It would be u prime v minus v prime u all over v squared. In this scenario, we're going to say that u equals the natural log of 2x plus 1. Therefore, u prime is 1 over 2x plus 1 times the derivative of what's inside, which is 2, leaving u prime as 2 over 2x plus 1. And also v is given as 2x plus 1. So then v prime is the derivative of that, which is just 2. So now I have u prime, v, and v prime, and I can assemble the derivative by using this formula as a template and putting all of those different expressions into these positions where they belong. The derivative in that regard will be g prime of x equals u prime, which is this quantity, times v, which is this quantity, minus v prime, which is 2, times u, which is this quantity, all over v squared, which is this quantity. Now, I'm a little bit out of my bounds here, but try to use your imagination. This is the numerator. I know you can see it. It's a little ugly looking, but welcome to calculus. All right, and notice how quickly and easily this happens. Look at this. Oftentimes with logarithms, one of the main reasons we like to play with logarithms in calc is because they make things knock out nicely. For example, look how easy that became. Now, g prime of x can be written much more simplified as 2 minus 2 minus 2. Let's start fresh. Sorry, friends. G prime of x can be written new as 2 minus 2 natural log of 2x plus 1 all over that quantity v squared. This right here is the derivative of it. All right. So that's example 2c. So far you've seen 4 great examples of how to use a natural log of x. Remember, the whole basis of the natural log is, let me get it out one more time because I have it here for us. The whole basis of the natural log is if you have a function that is a natural log, the derivative is 1 over x. If you have a function that's a natural log of something that can be that can be differentiated, then it's 1 over that and then times the derivative of that. And that's important to know. For example, here it's 1 over this, but then don't forget to, because of the chain rule, multiply by the derivative of that ultimately at the end. Let's do one more example of it. In example 3, we're asking you to use logarithmic properties to find derivatives. I don't like this color, it's glowing. Try it again. All right, let's take a look at this question now. I'm going to ask you to find the derivative of this. In order to do that, you'd have to go through a lot of work to take x to the 5th minus 2 quantity to the 10th power. That's really a lot of work. So instead, what we're going to do is we're going to start using those properties of logarithms that we're familiar with. Now, I want you to just kind of look with me one more time at this actual question. Take a close look at the question. We're asking you to use logarithmic properties to answer the question. So if you start doing this straightforward, you're not going to get answers as quickly and easily as we're expecting, but we want you to use logarithmic properties, and that's crucial. So let's take a look one more time at our logarithmic properties. And here they are. So for this case, you'll notice that we have a couple of different things being represented, okay? We do have the case of a natural log of two things being multiplied. That's something that I see right here. And we also have the case of a natural log to a power, which is what you see here. In fact, if you want, you could follow these ones because these are the ones in terms of natural logs, but they still follow the same ideas, all right? So that being the case, if I see two things being multiplied, then I know what I'm going to do is I'm going to write the two things separately, but I'm going to put a plus in between them. If I see something to a power, I know I'm going to take that power down and turn it into a multiplier in the front. So let's see if we can apply those rules right now to changing this logarithmic function using properties before I take the derivative of it. So that would look like this. First of all, I see that it's x times this quantity. So I have this could be the first thing being multiplied, and this is the second. Here's how you'd write that out. It's the natural log of the first thing, natural log of x, plus the natural log of the second thing, which is x to the 5th minus 2 quantity to the 10th. So this is what we call, well, depends on what textbook you're asking, but this is rule number 3 for the natural logarithms that we were showing in our PowerPoint slide. Next, let's apply rule number 5 to this piece because I have an uncomfortable exponent of 10. I can change this natural log. Instead of it being x to the 5th minus 2 to the 10th power, I can make it 10 times it like that and bring the 10 out in front. Now that I've done those two little things, I've made this question a lot easier to differentiate. First, we're going to apply the sum or addition rule, which says that I have a couple of things being added here, so I might as well take the derivative of each thing being added. The derivative of natural log of x is 1 over x. And the derivative of this is going to be, let's apply the coefficient rule, starting with 10 times something, right? Now the derivative of a natural log of something is 1 over that. And then multiply by the derivative of what's inside. What's inside has x to the 5th, which is 5x to the 4th, and then minus 2, which the derivative of the constants are all 0, so there is no derivative for negative 2. And this is your answer. To make it a little bit more practical and simplified, maybe what I'll do is I'll recognize that 10 and 5x to the 4th are both over 1 and put them in our numerator there. So I have y equals 1 over x plus 50x to the 4th all over x to the 5th minus 2. This is the solution we're looking for a question like this, where you find the derivative of a complicated logarithm that can be broken down using properties first. Something else to mention here that's really important. Please make sure you know when you can and cannot add fractions. In this situation, you could add these. You'd have to find a least common multiple, and it's a real lot of work, and it's unnecessary. This is a more than acceptable answer, so don't be afraid to give an answer that is the sum of many fractions. We're not asking you to do rational expressions and combine and add rational expressions with least common multiples. That's not part of what we're studying today. We're trying to focus on how to find derivatives of logarithmic functions, and it's okay if your answers turn out being many fractions in a sum or difference list like this. Don't worry yourself about combining them. This is more than acceptable, and this is the answer we wanted for example 3a. Example 3b is very similar. But again, it's going to employ all the different important rules that we've studied about derivatives. So it's going to be a little bit more, it's going to be a little bit more involved. This now we're looking at example 3b here, and we're going to do for the function f of x equals the natural log of, and in there we have a big fraction, including a cube root. And the whole thing is to the fourth. All right, so you're trying to find the natural log of this. Now I can apply the quotient rule and do a whole bunch of stuff here, but instead I'm going to start by applying the most important rules about properties of logarithms, starting with this exponent here, 4. That is rule number 5, where I'm allowed to bring the 4 out into the front because of the coefficient. Likewise, I have another case here of a division inside here. We have a story about if you divide, you can use subtraction with logarithms. Last but not least, we have a cube root here, and you know that the cube root means to the 1/3 power. So we have the same property here appearing again, but for a power of 1/3 in our numerator. The specific 2 important properties we're using are in this case, we're using this one, where we talk about how if you're taking the natural log of something with a power, you could put the power in front. And then we're also going to use, if you're taking the natural log of a quotient, like you see here, you can use subtraction and write one after the other. We're going to use those 2 rules together to try to expand and rewrite this function in terms of smaller logarithms so we could get an easier answer, okay? So the first thing I'm going to do here is I'm going to apply the power rule, which means bring the 4 out in front. So notice I'm writing f of x, not f prime of x. I'm not taking the derivative yet. It's important you make difference when you're taking your notes. So f of x of 4 times the natural log of that whole thing. And just copy it down. It only takes a minute. Write it out. You'll be glad you did. Now I have to apply the idea of the quotient rule, which is if I have a quotient, I can write it as subtractions. So the new function f of x will be 4 times, and now I have a whole bunch of stuff to multiply that 4 by. The first log looks like this, and the second log looks like this. Good. Now, remember, and I'll use a different color to illustrate this. Remember that this is the same as 3x plus 5 to the 1/3, isn't it? That's what the cube root means. It means the power of 1/3. So because of that, what I'll do is once more, I'll write, remember I haven't done the derivative yet, I'll write 4 times, and now this is going to be 1/3 times the natural log of 3x plus 5. All right, now I've expanded it all the way. I can't expand it anymore. I've expanded it first by breaking the 4, which was an exponent, into a multiplier by rule 5. Then I used the quotient rule, which is rule 4, to show that I could do this and this as 2 separate logs. And then last, once I did that, I wound up with a new power again, that again I could apply rule number 5, the power rule, by putting that 1/3 out in front like that. My last step here would be go ahead and distribute the 4 to this and distribute the 4 to that, which would give you something like this. F of x equals 4/3 natural log of 3x plus 5 minus 4 natural log of x squared plus 11. Okay, so what I've done here is I have not done any calculus. This is all algebra 2 work. This is all stuff from when you were in the 11th or 12th grade, learning a little bit about how to play around with logarithms, expand them so that they're in terms of more basic logarithms. If you look at what I have written here, this I can see myself taking the derivative of without very much difficulty. right? I think I wrote this wrong. The parentheses should be there. But this right here is the headache here. You see what I'm saying? So rewrite them out if you can. I'm going to write it one more time up here, and then we're going to talk about how to find the derivative of it. So now I'm looking at f of x as this function. Great. Okay, now recall that the derivative function, the derivative of the logarithmic function is like this. The derivative of a log is 1 over that expression. So now we're finding the derivative. The coefficient rule allows us to write the 4/3 and forget about it. Now the natural log, the derivative of that is going to be 1 over that times the derivative of what's inside. The derivative of 3x is 3. The derivative of 5 is nothing. So just to make it quick, I'll make it 3 over 1. And that's the first one. The second one, again, I'll do 4 times. And now here, I'll write 1 over that. And now the derivative of what's inside is 2x. And by the way, the derivative of 11 is nothing. Okay, good. So now, are there things that we can knock out? Let's see. This 3 knocks out nicely with that 3. And that's it. Nothing else is going to knock out at all. Nothing else. Remember, this is a numerator for 1 underneath, and so is that. So our final answer now, cleaned up, is f prime of x is equal to 4 over 3x plus 5 minus 8x over x squared plus 11. This is what we're looking for our final derivative. Okay, so you have some really great cases here, my friends, and I hope that you'll come back and review this video a lot when you're doing your WebAssign practice. It's going to be questions very much like this, and this should be elementary. There's no applications here. This is the straightforward mechanics of what it's like to use properties of logarithms to rewrite expressions to be easier to take the derivative, and also, of course, the notion of taking the derivative. Notice so far we've only done derivatives of natural logs. For the scope of our course, we're going to focus primarily only on the derivatives of natural logs, and we're not going to go further with trying to figure out the derivatives of things that have a base other than e. Those will be omitted from your practice and from your work. Okay, so examples 1, 2, and 3 are great cases of how to find derivatives of natural logarithmic functions. Let's do an application now. Let's talk about what it would be like to apply what we've learned to doing something in terms of a word problem. For examples 4 and 5, you'll notice both of them have functions in terms of natural logs. Again, we're going to only be studying derivatives of natural logs for quantitative analysis too. Let's read through example 4, and then I'll talk to you about how we're supposed to answer the questions. It's about lifespan. It says, assume that the average lifespan in years for people born from 1920 and projected to 2020 can be modeled by this function, where x is the number of years past 1900. Again, we have alignment of the data. For example, in 1975, when I was born, x equals 75, and it's important you know how to align the data that way. The first question reads, A, find a function that models the rate of change of the lifespan. Quite simply, find the derivative of the lifespan. The rate of change is ultimately the lifespan. So let's take a minute now and take a look at that function and take its derivative and see what we get for the rate of change for the lifespan. Here's the function. I'm going to use a capital L because that lowercase l looks kind of like a 1, and I don't like that, so I'm going to use a big L, so what? And we have some ugly decimals here. Okay, so we're trying to find the natural log. I'm sorry, we're trying to find the derivative of this function, noticing we have a natural log here. So the derivative will be L prime of x. And the derivative L prime is, first, let's take the derivative of this piece, because we're applying the addition or sum rule here, looking at 2 different things being added. What is the derivative of 11.249? The answer is 0. There is no derivative because it's a constant. This one, we have a constant 14.244 natural log. So because of the constant rule, I can write out 14.244 and forget about it, and now focus on the natural log. What is the derivative of the natural log? It's 1 over x. To make this a little bit more mathematically nice or friendly, we could put this on top and this on bottom. So here's your derivative formula. Really a pretty basic formula, ultimately. Let's take this part A, okay, is example 4. Let's see what else we're being asked in example 4. Now we're saying, does L of x have a maximum value for all x greater than 0? We can find that easily if we just graph it. Let's take a look at the graph. Okay, friends, I'm in Desmos now. I'm going to enter our function in and see what kind of behavior we have for x is greater than 0. Y equals 14.244 over x. What does it look like? Well, let's zoom out a little bit and get a good image of it. As x gets greater and greater than 0, in other words, as x carries on towards infinity, what is happening to the y values? We're getting closer and closer to 0, aren't we? So look at the question one more time now and see if we can answer it. The question reads, does L of x have a maximum value for x greater than 0? And the answer is it doesn't have a maximum value. The primary reason is not because of how it carries on toward infinity, but the highest value of y for anything greater than 0 is actually up here. And if you look, as we get closer and closer to 0, meaning like what about when x equals a very small quantity? It doesn't matter. It keeps going up and up and up, and it will never cross. So the answer is there is no maximum number. It could be 1 million if you have the correct thing, if you have the correct value in there. All right. Next part of our example is asking, evaluate the limit as x approaches infinity of the derivative. Okay, the derivative. So let's take a look at that. Okay, we're asking to find the limit, this is part C, as x approaches infinity of the derivative. What is the derivative? The derivative is this expression. Let's write it one more time. It's the limit as x approaches infinity of the expression 14.244 over x. Or you could have used this one, because when you do any number over x, we've established that the limit is going to be 0. Another easier way to look at it is to rewrite it looking like this. And then notice that you can do the limit of this and the limit of this and multiply them. The limit of this is 0. The limit of this is going to be, again, 14.244. What happens when you multiply them? So the answer ultimately for part C now is 0. And we know that because we understand that the limit as x approaches infinity of 1 over x is 0. And that's something we established a while back. The last part of example 4 has an analytic question. We're saying, what do the results of parts B and C tell us about the average lifespan? Now, all of that can be told using those two concepts, or using, of course, this concept, which is the easiest, our graph. The lifespan at the beginning is very, very high, and then as the years go by, it goes down more and more. And as we zoom out, you could see that that's what's happening, that the more you go on with X years, the lower you get. Now, when it's time for you to answer questions like this in WebAssign, the way you'll do it is you'll see, it'll say something like, what can you say about the function based on statements B and C? And if you look at a graph like I'm looking at now, it'll be a drop-down menu with like 4 or 5 statements where you select the one that is most appropriate. It's a matter of using your analytical and critical thinking skills to take the graph you're looking at and try to digest it and figure out how to answer the question. When it comes to WebAssign, the good news is you have 100 tries. So you can keep on trying to see which one it is, see if you guess it right the first time. And then your practice, you'll have many cases of it where you'll be able to guess over and over again. And it'll help you get comfortable and familiar with the way that logarithmic functions work and how to answer a question like that. But I would say when it says something like this, what do these results suggest about the lifespan? I would say don't look at the results B and C. More so look at the actual graph and see if you can use it to make heads or tails of the lifespan and to make some kind of statement that's practical about the way the lifespan behaves. All right, that's example 4. Let's take a look at example 5, which is the application of cost when we're doing an economics application. Suppose that cost function for X skateboards is given by this function here. C of X is the cost in dollars. Find the marginal cost when 100 units are produced and explain what it means. So remember the word marginal. What does marginal mean? Marginal means surprise, take the derivative, right? I mean, everything boils down to take the derivative. But if we have the cost, which we have here, C of X, and you want the marginal cost, it would be C prime of X, or the derivative of what you see. It works that way for profit, and it works that way for revenue, and it works that way for anything. If you put the word marginal in front of it, it means it's the derivative of that function. That being said, let's take a look at this function and find its derivative to get the marginal cost. When we're done doing that, we'll substitute 100 in for X to figure out the marginal cost when 100 units are produced. The function is C of X equals 18,250 plus 615 natural log 4x plus 10, like so. All right. Can we please figure out the derivative here? The marginal cost is C prime of X. So the derivative, of course, of any constant is 0, so this is going to kind of vanish on us. The derivative of this will begin with the coefficient rule using the 615, and then I'll focus on trying to find the natural log of this, which is today's primary lesson. The natural log derivative was 1 over this quantity, so it would be times 1 over 4x plus 10. And then don't forget, because of the chain rule, times the derivative of what's inside. The derivative of 4x is 4, and the derivative of 10 is nothing. So this turns out being just times 4. Now remember, the numbers that are in fractions, you can turn them into fractions like this, which leads us to believe that our numerator for the marginal cost, C prime of X, would be 615 times 4, which is 2460 over 4x plus 10. That's your answer right there. If you want, you could factor a little bit and simplify it like this. Sorry. 2 times 2x plus 5 all over 2 times 1230, and then the 2's knock out, leaving you 1230 over 2x plus 5 as your marginal cost. Again, you could have used this. This would have been fine, but either one of them, you know. Now, using that concept, let's go ahead and plug in 100 and get a solution. It'll be 1230 all over 205. And if we divide that, I'm getting a nice perfect 6. All right, so our solution for what is the average cost, not average cost, but what is the marginal cost for 100 units? The answer is 6. Now, the last question here is a conceptual one that I need to have a conversation with you about so that you're familiar with the idea. Notice it is asking this interesting question, explain what it means. When they say explain what it means, once again, remember what they're trying to say is there's a drop-down menu. Which of these statements is best describing what you mean by the marginal cost at 100 units? The marginal cost at 100 units is the cost is what it would cost to make 100 units to just make one more unit. And that expression, just make one more unit, or the cost of one more, that specific little wording, one more unit, I want you to connect that with the wording marginal. They mean the same thing. And if you are making 100 units, it will cost you $6 to make just one more. That's what we would say, something along those lines. Okay? So that's what you need to know, my friends, about logarithmic functions. Let's talk about exponential functions. You'll find exponential functions are 10 times easier than logarithmic functions. All right? So here we have our most basic logarithmic function. Our most basic exponential function, which we're going to use today, which is e to the x. The derivative of e to the x is simply e to the x, and this is the only time this will happen in calculus with derivatives. The derivative of something is itself that's what e to the x is. And that's part of the reason why e is such a perfect number that Euler figured out for us to use. Now, the good news is you don't have to write 2.7. You can just write the letter E, and we all know what you're talking about. You can also put E into Desmos, and they know what you're talking about. But from here on in, if you ever find yourself trying to figure out what the derivative of e to the x is, it's really very simple. The answer is e to the x. That follows, of course, with the chain rule. If it's e to an expression, then it's the same answer as you see, e to the expression. But don't forget to take the derivative of what's inside, which in this case is the actual exponent. Last but not least, if you're doing an exponential function that doesn't have a base of e, it's the same feel, except you have to make sure that you also multiply by the natural log of the base. So for example, if it wasn't e to the x, but instead it was 5 to the x, then you would do the same thing, but make sure that you multiply by the natural log of 5 when you're through. Let's do some basic examples of that first, and then we'll jump into the examples from the textbook. I'm going to give you some functions, and we're going to try to get derivatives of them. Here's some great examples. Let's say f of x equals e to the x. Okay, well then f prime of x is simply e to the x. Okay, let's establish that first and foremost. If f of x is something other than e to the x, like e to the 9x plus 7, then what you do is you say the derivative then is just what I'm looking at, e to the 9x plus 7. But don't forget to take the derivative of what's inside, which is inside 9x plus 7. The derivative of that is 9, making your final derivative 9e to the 9x plus 7. Okay, so can we remember that? You take the derivative of e to the x, it's e to the x. You take the derivative of e to anything else, it is just e to the whatever it was, but take the derivative of what's inside and multiply it after for the chain rule. Let's do some cases of a derivative of a number other than e to a power. If you want the derivative of 7 to the x, it's going to be 7 to the x. But don't forget to multiply by natural log of 7, because it's not e to the x, it's 7 to the x. And to compensate for it not being e, we have to adjust and correct it by putting natural log of 7 after it. That being said, if we had another case where we had a derivative of something like, and I'll choose another base just to show differences, say it's 3x squared plus 2, right? Well, that's going to be, in that case, f prime of x is going to be just what you see, 5 to the 3x squared plus 2, then times the derivative of natural log of 5, then times the derivative of what you see there. The derivative of 3x squared is 6x, which leaves your final answer being 6x natural log of 5 times, and you can put them in parentheses to make them clear if you want, it doesn't matter, 5 to the 3x squared plus 2, like that. Okay, it's a little bit sloppy, but I'm hoping that you'll understand what I'm saying. I'll write it one more time to make it really clear for us, okay? You want to combine together, let's just do that one more time. For the function f of x equals 5 to the 3x squared plus 2, you're going to say f prime of x is just what you're looking at, 5 to the 3x squared plus 2, but you have to multiply by a couple of things. Since this is not e, you have to multiply by the natural log of 5. And since the chain rule, you have to multiply by that, the derivative of that, which is 6x, which means your final answer really looks like this. You could write it in any way that you like, maybe like this. It doesn't matter really which order you put it in. They like you to put the exponent though last, like that. Okay? So now you have some great cases of finding derivatives of exponential functions, both with a base of e and with an alternative base of something else. Likewise, if you take a look at the graph of the exponential function, you'll notice it's very similar to the logarithmic function. Notice before we had the same image, but it was kind of up against the y-axis on the right of it, going upwards and to the right. It is ultimately a reflection of what you're looking at. All right? Now, here we have some great examples of finding derivatives of exponential functions. I like to work through all 4 of these examples with you. I want to show you how to do each of them, and they should become straightforward to you. I'm hoping that you're finding this lesson to be easier than the others because the answer is what you're looking at. The derivative of e is e, and that's the concept. So let's go through them one at a time. We'll talk about how you would go about finding your answers to these questions. The first one here is going to be example 1, which is there you go, which is y equals 3e to the x plus 4x minus 11. We're saying, will you please find dy dx? Remember, this is just another fancy way of saying find the derivative. Okay, we can find the derivative, no problem. 3 times e to the x. Well, the derivative, first of all, we have a sum of 3 things. We're going to do them one at a time. That's the sum and difference rule. Then here we have a coefficient of 3. We're going to write it and forget it. Now I ask you a very difficult question. What's the derivative of e to the x? It's e to the x. Notice it's an x up there, so I have to play games with the chain rule. What's the derivative of 4x? 4. What's the derivative of negative 11? Nothing. There's your answer. Example 2. We have part A. We're saying f of x equals e to the 4x cubed. Find f prime of x. So for this question, and notice we have an exponent with a coefficient and then an exponent within an exponent. Your handwriting really plays a role here. It's important that you're clear, and I like to write big so that when I do write small exponents, I don't have to squeeze, but this is what we're looking at as our question. Now, the derivative of e to whatever is, of course, going to be, like we promised, e to the same thing as you see there. But now, we're going to just make sure this is correct by multiplying by the derivative of what's inside, which in this case is this expression here, as per the chain rule. The derivative of 4x cubed is 12x squared. To make this a little bit nicer, I might want to put e at the end like this, because it has the most complicated exponent. And now you have an answer that's very mathematically appropriately written. Right. Our next example, we have some variables that we're not used to, s and t, but ultimately it does mean the same thing. Here, we're trying to figure out, we have s equals 3t e to the 3t squared minus, I can't even see it, or plus, yeah, plus 5t. Now, what they're asking you to do is find ds dt, which means ultimately take the derivative. I'm going to start with that 3, write it in there just the way it is because of the constant rule, I can forget it. Notice in this case we have a product rule. We have the product of t times this. So let's do u equals t, v equals e to the 3t squared plus 5t. So that means that the derivative of u prime is 1. And furthermore, the derivative of v prime is going to be just what you're looking at there, e to the 3t squared plus 5t. But don't forget to multiply by the derivative of what's inside, which this time is 6t plus 5. Making v prime, this long, complicated expression, 6t plus 5 e to the 3t squared plus 5t. This right here is v prime. And we're going to need that later on when we're assembling the derivative. Now, like I said earlier, remember, we do have a 3 there, and the 3 is a coefficient. We can write the 3 and forget about it and deal with it later, and just put together everything with t and e like that, okay? So I'm going to put this off to the side. I think I'll leave it right here. Okay. And now, to figure out the derivative, I'm going to keep on bringing it back and forth. To figure out the derivative, ds dt, I'm going to have to figure out first it's 3 times, and now what I need is, and recall what the formula is, I'll put the formula down here. If you're doing uv prime, it's uv prime plus v plus u prime v, right? So that means I need uv prime, which is t times this expression. I'll use brackets. T times 6t plus 5 e to the 3t squared plus 5t plus, and now I need u prime v. U prime is 1, and v is this expression, plus e to the 3t squared plus 5t. This whole expression is your answer. Now, what you want to do with that is up to you. You could carry on with that. You could simplify it. You could distribute it. You could distribute the t. You could put the e through everything. You could put the 3 through everything. You could do as much as you want. But ultimately, my friends, this is the ultimate answer. If I were you doing WebAssign, I would put this in just the way I see it. That'll usually, if you have it in that way, it'll come out just the way you're hoping it will come out. That one we would not have been able to do unless we began. I wish I could put this here somewhere. I think I can. I'm going to put it here like this. There we go. So this one really began with finding u. Let me move this over so we can get a picture of the whole thing. There you go. So this really began with finding u and v and u prime and v prime. And v prime took up a lot more time than we thought because it's long. This is the entire expression of v prime. Following this model right here, I can find u v prime plus v u prime and put it all together in this format, and now I have my correct answer. Whenever you feel like you're using too many parentheses, employ square brackets. Consider them in calculus like they're capitalized parentheses. They're bigger and better than parentheses. And use them. You'll use them a lot. Don't act like you're not going to use them. You can't get away with not using them. So draw them often when you're drawing out your derivatives. All right, friends, let's take a look at the next one. And the next one, we're asking us to do something of a quotient rule I can see going on there. This one reads, if u equals w over e to the 3w, then find u prime. Okay, we could do that. Notice for this case, we have, and don't let the u mess you up. We could have called it y, it doesn't matter. But what I want to think about here is this is u, and this is v. And according to our quotient rule, we have already established that the derivative of u over v is going to be u prime v minus v prime u over v squared. That, again, is our quotient rule. Using that, I need to identify u prime, which, since this is with regard to w, I'm going to say the derivative of w, like the derivative of x, is 1. To find v prime is the derivative of this expression, which is this expression. But don't forget to multiply by the derivative of what's inside, which is 3. To make v prime a little bit nicer, maybe I'll write it as 3e to the 3w. All right, so I have u, I have v, I have u prime, and I have v prime. Now I can assemble the derivative using the quotient rule, which is right here. The derivative would be u prime v minus v prime u all over v squared. Like so. Can we simplify a little bit? Sure, we can. Maybe it'll be nice to take this 1 out. Maybe I could stick this w in between the 3 and the e. Maybe I could figure out what 3w times 2 is. My ultimate solution here should read e to the 3w minus 3w e to the 3w all over e to the 6w. This is the answer we're looking for a question like this, simplifying it. All right. For our next case, we're going to ask you to figure out some derivatives using basic logarithmic properties first. Here we have an interesting function that's written like this. But it's kind of like writing an unreduced fraction. See, this is something that we've learned already. If you have e to the natural log of something, whatever that is, and I'll use a cloud as an example, the answer is going to be simply whatever that cloud is. We've established that way back. In other words, this statement is the same as y equals x squared. It's the same equation because it's kind of like a feeling like the e and the natural log knock out in a way. Okay, that be the case. What is the derivative? That's pretty easy. It's 2x. All right, so when you see something like this, whenever you see e to the natural log of, a little red flag should go off in your mind, and you should say to yourself, oh, wait a minute, I could just use whatever that is, so it's just x squared. This is a dead giveaway easy question. Don't let it trick you. When you see this, it's very easy, okay? So that's what it's like to take derivatives of functions that have e in them as a base. Let's do an example of a couple of examples of finding the derivative of something that has a base other than e, like for example, 4 or 5. Starting with example 6a, where we're asking you to figure out y prime if y equals 4 to the x. Now again, this is a constant to a power like e, but since it's not e, we have to compensate. The derivative will be, of course, what you're looking at, but to compensate, we multiply by the natural log of that base, and now you have your solution. Finding the derivative of an alternate base to the x is really very simple. Just don't forget to multiply by the natural log of that base to make it correct, and now you have the right derivative, all right? Now for 6b, we have a similar question, but we have the chain rule involved. For question B, we have y equals 5 to the power x squared plus x. And we're asking you this time to find y prime, where we have a exponent that is not just x, but instead it's something a little bit more elaborate. We'll write out, of course, the derivative. We know the derivative of an exponential function is just that exponential function, like you see here. And to finish up, I have to make sure that I do the natural log of 5, right? But also to finish up, I have to make sure I do the chain rule and take the derivative of what's inside. What is the derivative of x squared? It's 2x. What is the derivative of x? It's 1. And that's something people screw up a lot. Don't forget, the derivative of x is simply 1. And that's a big rule that comes up over and over again. Some students make the mistake of thinking it's nothing, like as if it was plus 12. The numbers get nothing. The letter x does have a derivative, it's 1. Now, can we write this just a little bit nicer? Maybe I could write the natural log of 5 first, times the quantity 2x plus 1, and finish up with times 5 to that funny power like that. This is what we would want as an answer. Again, you could put it in a different order. You could have even put it in just the way you see it there. And I'm sure that WebAssign would have accepted it and been very proud of you and happy to do that for you. All right. Now, as I'm going through these, I know that if you have questions, you'll be bringing them up, but I'm expecting that everybody's following. And if not, I know you'll be coming back and taking a look at our video, to try to get your answers as well. And these videos are posted on YouTube carefully right after your exam, right after your explanations, so that you can go back and look at them. Let's take a look at examples 4 and 5 now. Starting with example 4, I'll read it out loud, and as I'm reading it, I want you to try to use your wit and critical reasoning ability to try to come up with answers with me. Okay, we're going into example 4 now, and the question reads: when $100 is invested at 8% compounded continuously, the amount that accrues after T years, which is called the future value, is shown in this formula. At what rate is the money in this account growing at the end of 1 year? And how about at the end of 10 years? For a question like this, we're saying at what rate is it growing is code for find the derivative. So we're going to find the derivative of it. And when we're done finding the derivative of it, the next thing we'll do is we'll substitute in 1, and then we'll substitute in 10 and get some answers with a calculator. Let's focus on doing that now. First, let me jot down the actual function. The function is s of t equals 100 e to the 0.08 t. Very often in quantitative analysis, you see very uncomfortable numbers like 0.08. The easiest way to deal with them is to just write them larger than life so that you don't forget them, because the fact that it's a small quantity makes you feel like it's going to vanish on the page and all that. So just don't let it bother you. It's a number like 25, like any other basic number. Now, if I'm trying to find the derivative here, s prime of t, first and foremost, I notice that I have a multiplier of 100. That is the coefficient rule, so I'll just write the 100 and act like it's not there anymore. Next, I'm going to apply the rule of finding the derivative of e to any power, which would be the derivative is what you're looking at. It is ultimately this again. But don't forget, because of the chain rule, I have to take the derivative of what's inside. What's inside, once again, is a case of the coefficient rule. The derivative of what's inside is 0.08. Now, I could use my commutative property to think about 0.08 times 100, and I will get, of course, 8 if I bring that back. And now I have a nice formula for S prime of t. Now, if I'd like to figure out at what rate is the money in this account growing at the end of 1 year, that would be figuring out S prime of 1. If I wanted to find out at what rate is it growing at 10 years, that would be S prime of 10, which would be a matter of plugging those numbers in. So I would use my calculator for this one. For this one, I'm going to have to use my phone because I don't have a scientific calculator with logs or e. So instead, what I'll do is I'll do 0.08 and find the natural log of that. I could do that by putting 0.08 in the calculator first, and then I'll show you closely what it looks like. I don't know if you could see it, but this is e to the x right here, okay? Hit that, and you have your function, you have your number there. It's 1.083. Now that is the e. Let's multiply that by 8. The answer is $8.67. Let's do it again for this case. 0.08 times 10 is how I would begin. And it's, of course, 0.8. Now, e to that power is that, and I'll multiply that answer by 8, and I have $17.80. This application is very practical because you can use a calculator to answer questions about what the actual amount, a future amount of a deposit would be based on a exponential function like e. And we have one more great example. This one is about revenue. Let's read through it. As I read through it, I ask that you try to follow it with me. Okay. It's about a company called North 40. North 40 Incorporated is a manufacturer of wilderness camping equipment. The revenue function for its best-selling tent, the Sierra, can be modeled by this function, and we have a function there. And again, surprise, it has E in it, right? Where R of X is the revenue in thousands of dollars from the sale of X thousand Sierra tents. Find the marginal value of revenue when 75,000 tents are sold and explain what it means. Now, there is a curveball in here. Notice that we have X's in terms of 1,000 tents. X thousand, well, if we have 75,000, then we need to find R prime of 75. That is our end game, is to find R prime of 75. Let me jot that down. That's our idea. Trying to find R prime of 75. First, let's write down the function. The revenue function is R of X equals 250 X E to the power 1 minus 0.01X. All right. By the way, this is 1, and it's a little hard to see that. All right, so that be the case. Let's start by considering that R prime of X will start just being 250, right? And then I have two parts. This is a product. We have U is going to be X, so that means U prime is, of course, 1. Then we have V, which is going to be E to the 1 minus 0.01X, which means that V prime is, once again, that same quantity, E to the 1 minus 0.01X, but then times the derivative of what's inside, which is times negative 0.01. The problem is I'm trying to squeeze. I'm going to write it here like this. V prime then is going to be E to the 1 minus 0.01X times the derivative of what's inside, which is negative 0.01. This is very complicated and easy to mess up when you're writing it. Like I said, writing a big makes it much easier. All right. So now I have U prime, I have V, and I have V prime. To get the answer, I just have to assemble the derivative using the product rule. Remember, the product rule is UV prime plus VU prime. So it'll be 250 times all of that stuff. Starting with U times V prime, which is X times this whole expression. Let's write that out. I would probably put it together this way, negative 0.01x e to the 1 minus 0.01x, like so. And then the next thing, and that's u v prime, meaning x times all of this. I took the negative 0.01 and put it in front and included the x, like you can see there. And then last, we have plus vu prime. V is this quantity here, and u prime is 1. Anything times 1 is going to be what you see there. So it's just going to be times this expression, plus e, again, to the 1 minus 0.01x. This right here is r prime of x. Now, if you'd like to figure out specifically the marginal revenue, which is r prime of x at the case of 75,000 tenths. Remember, x is in terms of thousands of tenths. So what you're trying to find now is r prime of 75. To figure that out, I'm going to carefully plug 75 into every x position. Okay. For a question like this, it might be practical to just focus on that exponential e and find out just what that is first. Okay. So to figure out what that is first, what I'll do is I'll think about 0.01 times 75, right? And it's 0.75. And now 1 minus that, 1 minus 0.75 is 0.25, right? And now e to that, oops, 0.25 I said. And now e to that is this expression. So I can rewrite this now to be all of this stuff times that plus that. Let's write it out. I'm going to round it to, oops, what happened? I lost it. I'm going to write this out using 3 decimal points, 1.284, meaning that this particular piece is 1.284 now. And so is this piece right here, which makes the new math look like this. By the way, we have already established that this is 0.75 as well. So it's negative 0.75 times the quantity 1.284. And then plus 1.284. That's going to be $0.963 plus 1.284. So we add that plus 1.284. I'm getting 2.247. Now remember, again, that's in thousands. So look at the question. If my answer is 2.247, and we know that the revenue is in thousands of dollars, then how do I change 2.247 into thousands? I want to give you a conceptual idea. 2.247 thousands. Look at this idea with me. I want you to make this really, really easy. What is this in terms of thousands? Well, what if I told you it was 2,000s? Wouldn't it be 2,000? In other words, when I move this 1, 2, 3, oops, yeah. That's why this goes 1, 2, 3, and your answer is 2.247. Your solution. In thousands means go 3 spots, right? Well, I hope you had fun because I certainly enjoyed that. Lots and lots of fun derivatives, aren't they? I mean, I can't get enough of them. How about you? As far as I'm concerned, I would do this all day. But then again, they don't really quite pay me enough to do it all day. Anyway, that's all I have for you guys today. I hope that was informational and helpful. You had some great cases of you've had some great lessons here about how to find the derivative of every exponential function, whether it have a base of e, which is the easiest kind, or any alternative base like 4 or 5. We also talked about how to use those rules from logarithms to simplify functions before we take derivatives. We also walked around different applications like marginal cost, marginal revenue, and other examples using logarithms. I hope this was helpful for you. Now I'm going to ask you to go ahead and attempt WebAssign number 5. It is open for you on WebAssign. And I'll be here with you in case you need some help with it. Just reach out. Otherwise, I am going to close our lesson. and dismiss. But before I dismiss, let's just stop the recording and then open up the floor to any questions. Once again, thanks so much, my friends, for your attention to our lesson, and good luck with the practice.